Hi everyone. I will be talking on a survey on optimal path planning using RRT star based approaches. So let's start by understanding what is optimal path planning. Optimal path planning refers to find the collision free, shortest, smooth route between start and goal positions. This task is essential in many robotic applications such as autonomous cars, surveillance operations, agricultural robots, planetary and space exploration missions. Considering different applications and constraints of robots, optimal criteria could be based on one or more conditions such as shortest physical distance, smoothness, low risk, less fuel requirements, maximum area coverage, and low energy consumption. Hence, in perspective of path planning for mobile robots, optimal path refers to finding a feasible plan with optimized performance according to application specified criteria. So this is basic overview of optimal path planning. Now let's see what are different types of planners and how they compare with sampling based planners. So path planning algorithm are of vital importance for motion planning of mobile robots due to their numerous application in UAVs, forklift, surveillance operations, autonomous cars, medical, planetary and space missions. The initial complete practical planners such as road maps, potential fields, and cell decomposition techniques are unable to deal with dynamic and complex high dimension problems. Grid-based algorithms such as Dijkstra, Wavefront, A star, D star, 5 star are resolution complete and are computationally expensive for high dimensional complex problems. Evolutionary problems such as practical swarm optimization and colony problems are suitable for multi-objective problems. And other evolutionary algorithms such as artificial bee colony, bio-inspired neural network, these algorithms get trapped into local minima and bear high computational cost. Moreover, they are highly sensitive to search space size and data representation schemes of problem. Whereas sampling-based planning approaches are the most influential advancement in planning. Major advantages of sampling-based planning are the low computational cost, applicability of high dimensional problems, and better success rate for complex problems. Sampling place planners are probabilistically complete, that is, it finds a solution if one exists, provided with infinite runtime. Now let's see, now let's focus on RRT star algorithm and its properties to which the survey is related to. So RRT star, I will explain the algorithm first. So RRT star constructs multiple short paths randomly organized as tree instead of one long path. It originates tree from initial state Z to find path towards goal state goal Z. The tree gradually improves with iterations. In each iteration, a sampling process selects a random state, say random Z, from configuration space Z. The random sample is rejected if it lies in obstacle region. However, if the random is obstacle free, then a nearest node is searched in the tree according to some defined metric. If the random point lies in free space and is also accessible to nearest neighbor according to predefined step size, then a local planner insert it in tree by connecting the random point and the nearest neighbor. Otherwise, planner returns a new node by using a steering function and add it in tree by connecting it with the nearest point or nearest neighbor. This property of RRT to explore regions in free space is called Voronoi bias. A collision checking process is performed to ensure collision-free connection between the new point and the nearest neighbor. If the new point is found collision-free, then the nearest neighbor of new point are searched within the area of a ball of particular radius. Within the area defined by the radius, neighbor with minimum cost is selected to be the parent of the new point. Procedure of nearest neighbor search is similar to k-near neighbor problems to find out the best parent node with minimum cost before its insertion in tree. New node Z is inserted as child of the node with minimum cost. Further, the cost of near neighbor's parent node is also compared with the cost of the new node. If the new node gives less cost as parent, then rewiring process rebuilds the tree for minimum parent cost within the area identified by the radius. So this is the RRT star algorithm. You can go through it. And now I'll go through the properties of RRT star algorithm. The properties are that RRT star is asymptotically optimal. It converges to optimal solution in adequate runtime. It helps in solving high-dimensional complex problems. It is probabilistically complete, and its computational complexity is log n. So this was RRT star algorithm and its properties. Now let's understand the constraints. What are the constraints in path planning? So there are two types of constraints, holonomic and non-holonomic. The figure on the right shows non-holonomic constraints of car-like robot. So for a constraint to be holonomic, its condition must be expressible as equation connecting the coordinates of the points. A holonomic constraint depends only on the coordinates and time. It does not depend on the velocity. Examples, constraints involved in the motion of rigid bodies, constraints involved in the motion of point mass of simple pendulum, etc. If the condition of the constraints cannot be expressed as equation containing the coordinates of particles of the system, they are called non-holonomic constraints. In this slide, we see the non-holonomic constraint of car-like robot. A constraint on a dynamical system can be integrated, then it is said to be holonomic, and if it cannot be integrated, then it is non-holonomic. So these are two types of constraint and we will need them in further slides. So now let's look at single directional holonomic RRT star approaches. So there are a lot of algorithms that we'll go through now as this paper is related to RRT star survey. So single directional holonomic RRT star based approach generate path for holonomic robots and construct a single tree originating from initial state toward goal state to find path in search space. So there are various algorithms starting with RRT star FN. Now RRT star FN is fixed node. So RRT star FN algorithm is a memory efficient version of RRT star which forces a fixed number of nodes in the tree. But the limitation of this algorithm is that it gives jagged and suboptimal paths and lower rate of convergence to optimal path as compared to base RRT star. Then we have the RRT star smart. In this algorithm, two new feature intelligent sampling and path optimization are introduced. This accelerates the convergence rate with improved efficiency with respect to both time and cost. Then we have the informed RRT, which shows improved convergence than RRT star by proposing direct sampling technique based on ellipsoidal informed subsets. Finally, we have RRT sharp algorithm, which introduces a global replanning scheme to maintain promising nodes of tree to make fast convergence towards optimal path with low cost. So these were the single directional holonomic RRT star approaches. Now let's see bidirectional holonomic RRT star approaches. So in the slides, we can see there are four different algorithms for bidirectional holonomic RRT approaches. So first of all, bidirectional approaches generates two trees simultaneously from start and goal state, directing towards each other. Though bidirectional approaches execute faster for holonomic robots, However, when used for non-holonomic problems, they made very slow convergence. This is due to the fact that managing non-holonomic constraint using connect heuristic of bidirectionality do not guarantee the connection of both trees. Therefore, bidirectional variants of RRT star are considered suitable only for holonomic robots. So now let's look into these four algorithms. So first is the BRRT star, which is the bidirectional RRT star, which improves conversion speed and path refinement using sample rejection with an admissible heuristic. But the disadvantage of this algorithm is that it is computationally expensive and requires large memory. Also gives jagged and suboptimal paths. Then we have the optimal bidirectional RRT, that is optimal BRRT star, which introduces multiple heuristic based on different conditions to increase convergence rate of bidirectional RRT star. But again, use of multiple heuristic causes computational overhead. Therefore, we have IBRRT star. Now, IBRRT star is intelligent bidirectional RRT star, which uses intelligent sample insertion heuristic with minimum memory requirements, which improve the path quality as compared to RRT star and BRRT star. Then finally, we have HARRT star, which presents a human robot interactive planner using RRT star and homotopy algorithm. Actually, its results are basically trade-off between the computational efficiency and path quality. So these are four types of bidirectional holonomic RRT approaches. Now let's move further to non-holonomic and kinodynamic RRT star approaches. Now, non-holonomic robots are car-like robots which have to perform complex motions to achieve a particular direction. This phenomena also restricts geometry of the path. A car-like robot needs to change its position coordinates in order to rotate around its axis. It is underactuated due to the non-holonomic constraints imposed by the wheels. Therefore, non-holonomic path planning requires satisfying both internal constraints, that is the physical limitations of robot, and external constraints, that are the obstacles in environment. Further, if kinodynamic constraints arise, then it also affects path planning mechanism. Kinodynamic planning basically refers to the motion planning problem for which velocity and acceleration bounds must be satisfied. So let's go through these algorithms one by one. So the first one is adapter RRT star. This algorithm is an extension to RRT star with ensured asymptotic optimality with controllable linear dynamics in multi-dimension state space. Then we have the SRRT star, which is the spline-based RRT star, which presents geometric collision and dynamic feasibility function checking constraints during the tree expansion. It produces feasible, smooth, and cost-optimal path in 3D simulations. And then we have RRT star I. Basically, RRT star I initially is similar to RRT star. However, as soon as an initial trajectory is found, it adapts local sampling with Gaussian distribution and node rejection technique. So what happens is this generates smoother trajectory as compared to RRT and RRT star with improved path quality. Then we have the RTR plus CS star. This algorithm uses a local planner to generate feasible path for a car-like robot using circular arcs and straight segments. But the paths generated by this algorithm are not curvature, continuous, and natural. And therefore we have DTRRT star. So the DT-RRT star is basically the dual tree RRT star, which addresses the kinodynamic planning for high-speed mobile robots and produces practically feasible trajectories. Instead of using rewiring, it uses reconnect tree schemes to maintain child nodes with reduced computational cost. Then we have CARRT star, A CARRT star is cost aware RRT star, which addresses the problem of large number of samples by using two trees and cross entropies in RRT star. It produces energy efficient path in high dimensional space. Then we have PRRT star, which is potential function RRT star, which addresses the problem of high memory consumption and slow convergence by incorporating artificial potential field characteristics in RRT star. Then we have TRRT star. This algorithm integrates transition tests with RRT star for efficient extension of tree in a cost space. Finally, we have the rabbit star. This algorithm uses an informed global technique bit star with RRT star to find optimal path for narrow passages in high dimensions. So these were all the algorithms for non-holonomic constraints and kinodynamic RRT star approaches. Now let's go further and see what are the limitations and challenges involved with the state-of-the-art RRT star variants. The existing state-of-the-art requires improvement, particularly in terms of accuracy, efficiency, robustness, and path optimization. Optimal path planning is a challenging problem, and for online planning applications, convergence to optimal path is even more important. So as shown in this slide, here are some of the challenges involved in state-of-the-art RRT star variants. Slow convergence and large memory requirements, dealing with narrow passages, efficiency of nearest neighbor search, post-processing requirements, and dealing with kinodynamic complexities. Now, each of this point will be explained in detail in further slides. So let's move further and focus on slow convergence and large memory requirements. So here the issue is that RRT star requires large number of iterations and samples to avoid local minima, consequently increasing the memory requirements. Pure exploration also expands search space exponentially to find global optimum. Further, it is also expands trees in the areas of configuration space that are far away from the final solution. Hence, a large number of nodes in the tree are not good enough to contribute in the optimal path. These large number of nodes increase tree density by adding non-promising branches in the tree. This phenomena increases computational time and reduces the convergence rate. Now, how can we address this issue? Now, recent RRT star based planners have addressed this issue by exploiting search space using different sampling strategies such as direct sampling, goal bias sampling, intelligent sampling, two stage sampling, and disk based sampling. Few of them are shown in the slides. The sampling strategies shown in slides use different space exploration criteria. They try to limit search space using different heuristic to grow only promising branches and nodes in the tree. Another strategy performs guided exploration using APF to solve these issues. Moreover, different node deletion and node rejection techniques are also used to limit the tree cost by maintaining promising node according to a defined criteria. So this is how we deal with slow convergence and large memory requirements. Now further, how we deal with narrow passages. So the issue with narrow passages is that, conventional uniform sampling of RRT star reduces the probability of nodes selection from narrow passages. So how can we address this issue? The simply use other sampling methods such as Gaussian sampling and bridge sampling. Other approaches use heuristic dependent upon initial solutions such as informed RRT. Actually, I think there is a need to investigate the potential of these approaches to achieve optimization and reliability in narrow passages using real world experiments. Moreover, in context of kinodynamic constraints, problem of narrow passages is still an open research issue. Then we have the efficiency of nearest neighbor search. Now, the issue here is that computational complexity of near neighbor search in each iteration also grows as tree expands exponentially. Therefore, it is considered a bottleneck for efficiency and convergence. However, now, how to address this issue? So, to address this issue, maintain the efficiency by fixing maximum possible nodes in the tree. Other strategies that we can use is that most of the researchers have adopted is using smart data structures such as KD tree and quad trees. Now, the post-processing requirements. The issue is that RRT star based approaches generate suboptimal paths. Therefore, post-processing techniques are adopted to further optimize the path to address the issue. Two post-processing techniques usually adopted for path refinement are pruning and smoothing. Path pruning reduces the path length by removing redundant nodes. Local pruning is based on line of sight principle, whereas global pruning removes the myopic behavior of local pruning by pruning the nodes of entire path. You can see the figures of local pruning and global pruning in this slide. But what happens is that even after pruning, generated linear piecewise path is not feasible for UAVs and car-like robots. Curvature discontinuities in path make controller unstable and overshoots energy. This phenomena can cause mechanical aging, localization errors, and high energy requirements. The situation becomes more complicated when planning application involves heavy machinery such as industrial, defense, or agricultural robots. Then we come to the dealing with kinodynamic complexities. The issue here is that non-holonomic constraints require addition of robot's orientation to state vector. Thus, increased dimension, increased complexity of the configuration space exploration. Moreover, they involve solving differential equation and have more complicated state transition equations. Thus, planning for non-holonomic robots with kinodynamic constraint is more difficult and challenging than holonomic robots. Usually, path planners generate linear piecewise path, ignoring all the kinodynamic constraints and path smoothing. So we need to address this issue, and how we can do this is by resolving this issue by using the kinematic model of non-holonomic robot, which involves numerical integration. However, there is always a trade-off between computational efficiency and accuracy when using numerical integration. Recently, a spline generation approach is used to resolve these issues by encoding non-holonomic constraint in spline generation during path search process of planners. This process also reduced the kinodynamic planning to lower dimensional space. Correct selection of metrics for non-holonomic planning can also help. So finally, we come to the conclusion of this survey, and we can conclude that traditional path planning approaches are not feasible for non-holonomic cluttered high dimensional problems. RRT star proves to be worthy of dealing with such problems. RRT star variants have mostly addressed the issue of suboptimal paths, slow convergence, and high memory requirements. However, generalization and reliability in context of online planners and non-holonomic constraints are still open research issues. Use of spline with RRT star has opened new horizon of research for path planning of non-holonomic robots. And finally, curvature continuous paths for high-speed vehicles, dynamic environments, and computational efficiency is another thriving area of future research. That's it from my side. Thank you. And this was the survey that I have cited. Thanks a lot.